Okay, so we're going to look at transformations. Transformations are a way of changing the look of a function. So you've got translations, which slide a function left, right, up, or down. And then you've got stretches, which change the shape of the function, either horizontally or vertically. So we're going to look at vertical transformations first. Okay, and so here is, when we're looking at function notation, here is what we're going to be looking at. We're going to say VT is a vertical translation, and VSF is a vertical stretch factor. Okay, so given f of x is some function, if you wanted to graph y equal to a times f of x plus d, then that is a transformation of f of x where this new function y equals af of x plus d has been vertically stretched by a factor of a and vertically translated d units up, okay, or down. So d, if d is negative, it's down. If it's positive, it's up. So this may not be totally understandable at the moment. We're going to go through some examples to hopefully explain this a little bit. So if you have some function f of x equals x squared. So for f of x equal to x squared, we know what this graph looks like. We're going to look at this function because we know what the transformations of this look like vertically, and we'll be able to verify it just by what we previously know. And we're going to then work with this new notation to see if it works. Okay? So here is a graph of y equals x squared with a short table of values. Okay? So what we want to look at are some key points here. So three key points are, well, when you plug in x equal to 0 and you square that, you get y equal to 0. When you plug in x equal to 1, you square it, you get y equal to 1. When you plug in x equal to 2 and you square it, you get y equal to 4. And when you sub in the negatives of those, you get the same y values. Okay, so there's some symmetry in this function. So we're going to use these as three key points in this. We're going to see what happens when we leave 0, 1, and 2 fixed for the x coordinates, so we can see what happens to the y coordinates, which tells us what happens vertically. Okay, so if we look at this function here, y equals 2f of x, well, from this notation here, a is 2. Okay? Now, more explicitly, so this is in function notation, more explicitly, this just is y equals 2x squared. We know what the graph of y equals 2x squared is. It's a vertical stretch of this by a factor of 2. But let's take a look at this a little bit more strategically. Okay, so if we look at the table of values for 0, 1, and 2, well, y equals 2 times what f of x was over here. So f of x was 0, 1, and 4. Now we're putting those here, and we're multiplying it by 2. And we get 0, 2, and 8. And you can see that the y values are double what they used to be. That's what the effect of that 2 has on it. Okay? So when we graph it, we're still going from negative 2 to 2 for the x values. That hasn't changed. But the y values, instead of going from 0 to 4, now go from 0 to 8. So this has been vertically stretched by a factor of 2. Okay, so it used to be a height of 4, now it's a height of 8. All right, what if we did translation? Okay, so if we look at this one here, we're taking f of x and we're adding 2 to it. So we're taking the old y values and you're just adding 2. Well, we know what this looks like. X squared plus 2. We just take the quadratic here and we shift it up 2. The vertex is at 0, 2. Okay. Now, this is what the graph looks like, and this is what we're doing. We're taking the old y values from here and we're adding 2 to each one of them. Okay? And we get 2, 3, and 6, which just doesn't change the shape of this like this stretch did. It just shifts it up 2. Okay. what if we then put a couple of them together? Okay. For example, y equals negative 2f of x plus 3. Well, that's just negative 2x squared plus 3. And the vertex is still at 0 and 3, but it's been flipped down, so it opens down because of this negative 2, and it's vertically stretched by 2. So we know this from what we previously knew about quadratics. Let's see how this works in this notation. So we're taking the old f of x values, which was 0, 1, and 4, from here, so 0, 1, and 4, and we're multiplying them by negative 2, and then adding 3. So this becomes stretched by a factor of 2. Okay, so it used to go from 0 to 4, which was a height of 4. Now it goes from 3 to negative 5, and that's now a height of 8. Okay, so it starts at 3, goes down to negative 5. That's a difference of 8. Okay, so it has been vertically stretched. The negative means it's going to be flipped vertically, so it takes all the old y values and now makes them the opposite sign. Okay, and you have to do the multiplication first, so it has this vertical stretch and flip first. Okay, and then the 3, you're going to add 3 to it, so it shifts it all up 3. Okay, so this does have the effect of being stretched vertically by 2. The negative here means a vertical flip, so a reflection in the x-axis. And then the 3 means then translated up 3 afterwards. Okay. Now to do this more generally, if you wanted a point-wise formula for any function, okay, all you're doing is you're taking, when you have f of x being transformed to a times f of x plus d, okay, in the above one it was a was negative 2 and d was 3. Okay. When you're doing that, all you're doing is you're taking the old coordinates, the old points, leaving x fixed, multiplying y by a, and adding d. Okay, so for example, the one we just did above, for f of x equal to x squared, going to y equals negative 2 times f of x plus 3, which is what we had at the top here. Okay, so that's the same thing. We can then write a point-wise formula and plug in some key points. So the x and y point, go to x, stays the same, negative 2 times y plus 3. So let's take some key points from the quadratic. Key points from the quadratic, y equals x squared, are these. Now when you plug them into this formula, all the x's stay the same, so 0, 1, 2 will stay the same. But we're going to take the y coordinate here and plug it in for y, so negative 2 times 0 is 0, plus 3 is 3. So there's that point. Okay, and is that a point on the graph above? Yes, 0, 3, that's a point. Okay, and the point 1, 1, well, the 1 stays the same for the x. Take the 1 here for the y. Negative 2 times 1 is negative 2, plus 3 is 1. So we get that point. So is 1, 1 a point on this graph up here? 1, 1, yes it is. Okay, 1, 1, that's a point. And then 2, 4, so 2 stays the same, the 4 goes in here, negative 2 times 4, negative 8 plus 3, which is negative 5. Okay, so is 2, negative 5 a point on there? Yes it is. 2, negative 5. Okay, so and with those 3 points, using symmetry, you can plot the points on the other side. Okay, and you've got the graph. So this is an easy way of doing this, and it'll be useful when we do horizontal and all of them together as well. So another example is to transform this one So here's a function. There's no explicit formula for it. It's just 3 lines. Okay? 3 lines, and you can identify some key points here. So that's at -3, 0. This one is at 0, 4. This point is at 4, 4. And this point is at 5, 2. If you had to do this transformation to it here, well, then you need to come up with a formula. You can pause the video now and try this. But you need to come up with a formula for that so you can transform those points. Okay, and this would be the formula. So x stays the same because there's no, it's just the a out in front here and the d here. And then it's -2 times y minus 1. Take the 4 points, apply that formula. Okay, so -3, 0, 4, and 5 all stay the same. When I plug in 0 here, I get -1. When I plug in 4, I get -9. Plug in 4 again, I get -9 again. When I plug in 2, I get -5. You plot those 4 points, draw it, and this is the graph you get in blue here. So this graph, does it look like it's been flipped vertically? Yes. Does it look like it's been stretched by a factor of 2? Yes, it is double the height. And does it look like it's been translated down 1? Yes, it does. Okay, so that is vertical transformations. And let's see if we can try another one. Okay, so the function y equals 1, or f of x equals 1 over x. Recall, this looks like this function here. Okay, so some key points on this are 1, 1, -1, -1. If you subbed in x equal to 1, you get 1. If you sub in x equal to -1, you get -1. So those are key points. Cannot divide by 0, so a vertical asymptote there. And no matter what you plug in here, this function will never equal 0, so you have a horizontal asymptote. There's 2 key points. Now, there's other features to this. So there's 2 other features, the horizontal asymptote and the vertical asymptote. So what we do is we can describe the horizontal asymptote. Well, the x doesn't matter. It's the y value. The horizontal asymptote, the x is everything. But the y can only be 0. And then the vertical asymptote, well, the x can only be 0, but the y is everything. Okay, there's no specific point there. Now these aren't points on the graph, but they're features of the graph that we need to consider when doing transformations. So if you wanted to graph, say, this function here, well, that comes from a 1 over x function. So what transformations has happened to this? Well, it really looks like this, -2 times f of x plus 1. And the reason for that is because you can factor this -2 out, and then it's -2 times 1 over x. And 1 over x is our parent function, f of x. Okay? So this is now our function notation of the transformations. And we can tell that it's going to be vertically stretched by 2, vertically flipped with -1, and then vertically shifted up 2, or up 1. Okay, so there's the formula for it. Here's what happens to the points. Okay, so xy goes to x, -2y plus 1. Those 2 key points that we had up here become these points here. And then the horizontal and vertical asymptote get affected this way. You plug them into the formula. If there's no x value, it stays no x value. If there's no y value, it doesn't affect it at all. Okay? And then you graph that, and you get this graph. And does it look vertically stretched? Yeah. Does it look translated? Yes. And that's it for vertical transformations. The next video will be on horizontal and both of them combined.